In this video, I'm going to give a summary of this paper in which reinforcement learning is used to improve matrix multiplication algorithms. They were able to match the state of the art and improve in some cases, like in one case that hasn't been improved in 50 years. And not only they improve over the manually optimized algorithms for small matrix multiplication, but it was able to scale to matrix multiplication sizes that could not be optimized by humans. As you may know, the importance of matrix multiplication is huge. It is used in transformer attention layers, in fully connected layers, in convolution layers that can be converted to matrix multiplications, FFTs, etc. So giving an improvement in this is huge. The key of this work is turning the optimization of matrix multiplication into a game so that it can be optimized by the reinforcement learning search. And the way that this is done is by factorizing the matrix multiplication into multiplication decompositions. So you have a set of decompositions that are added, and each of those decompositions becomes an action. So we're going to see more details about this. Previous work focused on human search or continuous optimization and combinatorial search that rely on human designed heuristics. And here's how the problem is handled. The first step is to map a matrix multiplication into this 3D tensor. So basically you have 3 planes. Each plane is going to correspond to one of the dimensions of all the elements. For example, this is A1 to A4, this is B1 to B4, and C1 to C4. So when you multiply the elements, for example, A1 multiplied by B1, then you have one of the elements for C1, then that will be a B1 and A1. So you have it in, this is for A1 and this is for B1, so you have this element, but you also have A2 plus B3, so you add those, so that will be a B2 plus A2, so that will be something around here. It might not be visible, but it might be somewhere around here. So that becomes the value of C1. So basically this is each element in this 3D tensor is going to be a 0 or 1. And the dimensions, as I mentioned, you basically it's the number of elements in here. So it should be n squared. Once you have this 3D representation of the matrix multiplication, you find a decomposition. So the decomposition is basically, you can see it as an algebraic factorization. It's like in algebra where you move statements, terms around, and you can factor them and in this case you factor them in a way that you minimize the multiplications, because additions are way less expensive than multiplications, so you're trying to minimize the multiplications. And the way that they do it is that they have a set of factors. You can see from M1 to M7. Each one of these factors has a matrix multiplication. No, sorry, just a scalar multiplication. So each one of them corresponds to a column in here. So, and this dimension corresponds to A, to the first matrix, and this dimension corresponds to all the elements in the B matrix. So this represents if you are going to add that element into the factor multiplication. So in this case, A1 and A4 are going to be added, and here B1 and B4 are added, and both terms are multiplied. So once you have this factor, then yeah, for example, let's take another one. Let's take this one. This will be the number 4. So it will be A4 multiplied by the negative of B1 and B3. So A4 multiplied by B3 and the negative of B1. So once you have all these terms, in order to come out with the output value of the matrix, you basically add those terms. So yeah, so in this case, for example, C1 is going to be, these are correspond to M1 through M7, and this is the C dimension. So for C1 it's going to be M1, M4, negative 1, M5, and M7. So etc. So this will be M3 and M5 for C2. So notice that this factorization, the multiplications are going to be concentrated in the number of terms. It's going to be proportional to the number of terms. So each action in the reinforcement learning agent corresponds to one column here. So you're going to receive a penalty of -1 for each action that you take. So that is going to encourage the agent to factor this, do this decomposition in the least number of columns. So the less columns, the less multiplications, and the more efficient it is. But in addition to that, it also includes in the reward the runtime in a particular hardware, so you can optimize for a particular hardware without knowing in advance the hardware architecture. That's something that comes for free by using reinforcement learning. Okay, so basically at the end you add those and you get the metrics at the end. So this is another visualization of what I just mentioned. And this visualization came from slides from a YouTube video that I have in the description of this video, in addition to the Yannic video on this paper, which is very good as well, and also the link to the paper itself. Okay, so you can see the U and V's, each column are a vector. They are vectors. So when you multiply, which this is a multiplication, these two vectors, you're going to have a two-dimensional array, a matrix. So when you multiply that matrix by this third vector, then you got a tensor. So you finally got a tensor. So in the end, you're going to get this three-dimensional tensor, and they can be added. And then at the end, when you add them, you're going to have this 3D tensor, which is a representation of the matrix multiplication here. So each step, as mentioned before, is an action by the agent, and also they can serve as training. So as I will mention later, they are going to use a set of predefined games that are used for training, in addition to more successful games that they find along the way as they are training the agent, the experience that they find. So they randomly pick between the two and use to train the network. So like in other deep learning problems, data augmentation is important to get more data. And as you can see in image processing convolutional neural networks, in which the images are flipped, inverted, rotated to get more data, they do something similar in here. They basically change the basis of the input tensor, the input 3D tensor, but in addition, you can see that you can change the order of these additions. So that's another strategy that they use to data augmentation, as far as I understand. As mentioned before, this matrix multiplication decomposition is framed as a game, so that we can use reinforcement learning, and at the end there's going to be a penalty of -1 for each decomposition to encourage finishing it as soon as possible. And at the end, if you get to the correct solution, you're going to get a reward that is proportional to the negative of the runtime. You want to minimize the runtime, and of course, if you don't reach a correct solution, you get a big negative penalty. And the state space of this is huge. So it has more than 1012 actions for most interesting cases, and this is much larger than the chess and Go games for which AlphaGo was made. So this Alpha Tensor agent developed here was based on AlphaGo. It's an improvement. I had to improve, of course. The state space is bigger. I already mentioned this. Basically, the agent is going to look for decomposing the matrix multiplication and exploits the symmetries of and makes use of synthetic train games, which are pre-made games that perform well. The advantage of using a reinforcement learning approach with Alpha Tensor is that they can reach to a larger state space for bigger problems than humans and combinatorial search is capable of doing, and it's basically able to tackle this NP complete problem, and improves as mentioned, the Strassen algorithm for a 4x4 matrix multiplication that hasn't been, to their knowledge, improved since 1969. And it also is more efficient because it optimized for the runtime of a particular hardware target. Okay, so this is what they do. The game is done as follows. You have the matrix multiplication, you turn it into a 3D tensor, and then select the composition, subtract it from this tensor, and keep doing that until this becomes 0. And once you get to 0, or you reach the maximum of actions, then you get choose a reward in there. So the positive reward for completing is only done once you make sure that you have a correct decomposition to guarantee the correctness of the proposed actions of the agent. So this is algorithm number 1 is basically stating the formula, which is basically each element, each term in here is an action, and this is a vector, vector and vector and vector, and when this is a tensor product, when multiply these two vectors you get a matrix, and when doing this product here you get from the matrix and vector you get a cube, a three-dimensional tensor. So basically this is basically what we saw already, that the u terms are added, multiplied by the corresponding term in the input matrix, first input matrix multiplied by the u. The same thing is done by the b, and multiplied by the factors of the decomposition, and then you got the m term, and then that m term is just added in here. So these m are the ones that carries the multiplication in here. So here's the agent. The agent is gonna have two components. One of them is to get the experiences, to actually get the successful decompositions, and another component is for the training. For as mentioned before, there's going to be a database of pre-generated synthetic demonstrations, which are generated offline before the training and are demonstrated to perform well. So in addition to that, when you get experiences of finding new algorithms, you're going to collect them there from the reinforcement learning training. And I understand that once you have discovered a better optimal algorithm, you're going to take it from there at the end. I did not saw him, the author mention that explicitly, but it's kind of might be obvious. So so for getting the actions, basically you, as mentioned before, the change of basis is performed for data augmentation, and it's going to use a Monte Carlo tree search, and the Monte Carlo tree search is going to use the policy and the head. The policy, you can see it as the critic, and no, sorry, the policy you can see it as the actor, and this as the critic. So based on them, you get a tree simulating the action space, and this action space is huge. So basically, by using the trained neural network, you're gonna prune it, and eventually you select one action that maximizes the reward. And not only that, the Monte Carlo tree search is also going to encourage exploring areas. It's going to keep account on the actions that have been taken. So that is going to be used to combine the maximization of the reward with the exploration, which is something common in reinforcement learning. So once you select the action, you're going to change the state of the cube, and that's going to be fed for the neural network for the next stage, and the previous action is also fed. The neural network is going to take as input the input tensor, but also the previous action and some scalars, and then etc. You find the decompositions until you find a successful game, and you put it there. And once you have that's the experience part, and this is parallelized in a GPU, but also the training is parallelized as well. So you're gonna randomly select a sample and feed it into the network, and you're gonna train it. And probably I did not saw him talking about the what formula is using for optimization, but I understand that if it behaves like an actor critic, it might be used the policy and value to compute the gradient for the parameters in here, and optimize improve the parameters for the policy to maximize the reward, and for value to minimize the error of the predicted reward. So this is gonna give you the action, and this is gonna give you the expected cumulative reward, like an actor critic agent. So in this slide, taken from one of the videos in the reference in the description, you can see that yeah, that video actually, I understand, was made by one of the authors of this paper, Hassabis. I think Hassabis is the name. So you can see that you have a 5x5 for this one. When a 4x4, the Strassen version is the state space smaller than Go, but when you go to 5.5, it is a larger state space. And in the paper they show the results that they are able to optimize way beyond that as well. Yeah, and here basically the author mentioned that yeah, the input is an input 3D input tensor where the elements are 0 or 1 of this size. I mentioned that before. And once you have the decompositions, you basically just add them with this formula, and this is basically tensor product, and all of these are vectors. And the game initially, as mentioned before, starts with the tensor, the 3D tensor that expresses the matrix multiplication, and the agent is going to select an action, which is a trio of vectors, and they are subtracted. And you apply the tensor product in these trio of vectors and subtract it from the current tensor, and that's how you get the next state. The goal of the game is basically to reach 0, and when the player reaches 0, basically the decomposition factors are going to satisfy this formula, and this guarantees correctness, and there's a R limit, a rank limit to let's say that you have a 100 rank. At that point you know that you lost the game, so you stop. As mentioned before, for each decomposition you got a penalty of -1. This is to encourage the agent, which is trying to maximize the reward, to take as less step as possible, which reduces to less rank and less multiplications. And the game terminates after that limit, and if the agent receives an additional reward, if it is an upper bound of the rank of the terminal tensor. My bad. This is the penalty is the upper bound of the rank of the terminal tensor. So if you arrive to the end with a non-zero tensor, it means that you didn't find a good decomposition. So you will receive this bad penalty. And of course, these setting as is are going to optimize for rank to minimize the multiplication, but also you can include in the formula the runtime for a particular hardware target. Okay, so yeah, the constraints, the entries in the decomposition are constrained to this -2, -1, 0, and this avoids the issues with finite precision of floating points. But in theory, it could be anything. It could be -infinity to infinity, 0 point something. It could be real numbers, but to make the problem easy, they chose those. And alpha tensor, an agent of alpha 0, which basically achieves superhuman performance in the game Go. Strassen Yogi it was basically this, as mentioned before. Alpha tensor is based on alpha 0 and had to be improved to make this possible. And the Monte Carlo trace search is used to select the decompositions as well. The input is a state, basically the tensor, and also it takes as an input the previous play, and also some scalars. And outputs a policy and value. Policy is the action, and the value is expected cumulative reward. Policy provides a distribution over potential actions, and the space is huge, so they rely on sampling on this, using this Monte Carlo tree search based on the results of the network. And also at that point you encourage exploration as well, using as mentioned before, the number of actions, number of times an actions have been taken. and the value provides an estimate of the distribution of returns the cumulative reward for the current state. So here's the network architecture, and this is overall architecture. So you have the input tensor, and you have a history of tensors. So you have a series of tensors for each transformation. And the torso is going to give you the embedding. And that is going to feed the policy head and value head, which are transformers. This has a transformer side that is common to both the policy and the value. And the policy, I'm going to give more details about that, but in the end, these are the actions, the candidate actions with their distribution and estimated cumulative reward. And within the torso that we do the embedding of the tensor is going to be broken down in 3 planes. And each plane corresponds to all the 3 combinations of pairs coming out of the dimensions. So for example, if you have x, y, and z, you're going to have x, y, y, z, and x, z, each of these 3 planes. Initially, for these planes, they have a 3rd dimension for the batch size, and they go through some transformation and they turn it into a cyclic dimension here, and eventually they collapse down the spatial dimensions into 1 dimension that is fed to the policy head transformer. So here is the transformer that they use for the policy, and you can see that it is fed the embedding, and you can see that it has 3 of them. So these are for the decomposition, I understand. No, my bad. I understand that this is for each action taken. So you're gonna pass the same thing, the same embedding, and it's gonna have a cross attention that is gonna pay attention to the embedding, that is the input tensor, but also to the previous play. So initially this play is empty, and this the play here is passed to the next stage, and while taking the same embedding to predict the new action. And notice that initially when there's no previous action, that is the only time that the value head is calculated. It's not calculated for the other ones. They mentioned the axial attention generalizes as and is more efficient and a naive self-attention. They exploit tensor invariance to disregard the order of rows and columns. The policy head is going to have an auto-regressive model, and the value head is going to be a multi-layer perceptron. I understand that should be a fully connected layer of matrix multiplication. Although tensor decomposition is NP-hard, the inverse of constructing the tensor from rank 1 factors, which is what this problem is doing, is elementary. So they use this to create the synthetic examples offline. They generate a large data set of tensor factorization pairs by sampling this and basically assembling the tensor using the same formula before. So they train the network using this synthetic demonstration, using supervised loss, that is imitation by training, and standard reinforcement learning loss, that is the decompositions that they take along the training. And they mentioned that mixing these strategies of supervised and reinforcement learning and semi-supervised, maybe, they basically are more effective together than separately. This is despite the discrepancy of properties between these two groups of input games. Yeah, maybe for the context I can show an image. So if I go back here, so this is what I refer. These are the ones, the reinforcement learning based training, and this is the synthetic ones that supervised and reinforcement training. So that's what it is referring there. Yeah. So yeah, as data augmentation, they basically, since factorization are order invariant, they swap the order randomly to get more data and also do the change of basis. And the experiments were done for sizes below 5, although they go also to below 12. These are the ones that I understand that are not comparing against human optimization. So when the matrix sizes are large, they said that they just apply recursively the optimizations for smaller matrix multiplication, but I understand that the reinforcement learning approach that they're presenting here doesn't have to do that, because it's doing the decomposition at the big level. That's something that is hard for humans. Okay, so here are the results. So we can see that the Strassen, the one from 1969, was improved in the modular tensor ranking. The standard tensor ranking, I think it mentions here the difference, the modular arithmetic and standard arithmetic. So there are two ways to compute the rank, and I think the best known is computed in some other way. I don't know, but in the end, this should be proportional to the matrix multiplication. So they were improved by 47, but they mentioned also that the runtime is better than Strassen, because Strassen is not optimized for a hardware target, while the reward of this reinforcement agent can do that. And yeah, so they were able to match other algorithms. John Hopcroft algorithm was able to be matched. And also this algorithm was improved by 4, but when you get to higher tensor values, those had a significant improvement. The humans cannot get into the sizes of these arrays. So for example, the one of Strassen that was improved, you can see it in here. It's a 4x4 matrix multiplication, and you can see that we have 47 multiplications. As mentioned before, each term has a multiplication. And for the case of a 5x5, this is a 4x5 multiplied by a 5x5, and you can see the improvement here. In this case, we get 76, which are basically improved by 4. But also, when you do these decompositions, it's not just the number of the rank, but also the factors that are used in these operations. Those can have an impact as well on the particular hardware target, as the results are going to show later. So this is the result for the big matrices. So when you see something like this, is because, okay, this is a 6x7 matrix multiplied by a 7x9 matrix, and this is the discovered rank and the known rank. So you can see the improvement. It is more common, the improvement, as the matrix get bigger, and this is strategy recipe chosen. A crucial aspect of alpha tensor is the ability to transfer knowledge. So you optimize for a particular matrix multiplication size, and this scale, that knowledge can be used for other matrix multiplication sizes. And I understand that applies also for hardware targets. So for example, if you train it for a TPU, then you want to train it for a GPU, then you can transfer the knowledge, but of course you have to do fine-tuning for the GPU. And of course, it is scaling, and there was no to the best of their knowledge, there's no previous approach that was able to handle a T/4, the size 4, which is 10 to the 10 larger than T3. Yeah, so they were able to do this with larger tensors. One of the main advantages of this work is basically being able to optimize for a particular hardware target, and as mentioned before, this is simply done by adding a factor in the reward to be negative to the runtime. So you want to maximize the reward, so the less runtime, the less the negative value, and you can easily optimize for that particular target without knowing anything about it. So they train for a couple of targets, the GPU V100 and the Google Tensor Processing Unit version 2, and they used JAX for the benchmark, and they were able to outperform Strassen square algorithm. As mentioned before, it outperforms, although it has the same theoretical complexity as Strassen square, it outperforms in practice because this algorithm was optimized for the particular hardware, while Strassen square was not. And you can see the performance difference in these numbers. In the left is the GPU, and the right is the TPU. And the speedup is relative to the corresponding optimal algorithm. For the case of the GPU, is the CUDA blast. And so basically you can see that Strassen has a big speedup, but the alpha tensor one has a even bigger speedup. And one interesting experiment that the author tried was that they tried the TPU optimized algorithm and the GPU optimized algorithm both in GPU, and TPU, and you can see that the GPU trained algorithm outperforms the same alpha tensor algorithm. The alpha tensor optimized in GPU outperforms the alpha tensor optimized in TPU, and the opposite goes happens as well. The alpha tensor optimized in GPU is outperformed by the alpha tensor optimized in TPU. So optimization, this reward of the negative runtime, does make a difference for the hardware target. So it was mentioned in the paper that this strategy of reinforcement learning is not only good for matrix multiplication, but can be applied for other problems as well. And here it shows the cyclic convolution operation in which it finds the discrete Fourier transform and the inverse discrete Fourier transform in finite fields. So that's another application of this. You didn't give much detail about this. The alpha tensor is using the adaptive momentum optimizer with the coupled weight decay to optimize the parameters in the neural network. Monte Carlo tree search consists of a series of simulated trajectories in which the states are the nodes and the edges are the actions, and it's basically simulating the traversal from the root state to the a terminal state to select the action, and it's gonna basically try to explore actions that are not frequently explored. So it looks for exploration and maximizing the reward as normally in reinforcement learning. So here's the formula that they use. N is the visit count, Q is the action value, and the reward, I understand cumulative reward, and this is the policy, a policy probability. So in here you can see that it's a factor that measures the frequency of that particular action. So, and this, you have a factor that is going to control the exploration rate. I understand that if this follow a regular reinforcement learning approach, initially it's going to do a lot of exploration and then gradually decrease and increase and by decreasing this, you increase the maximization of the reward. So this is the cumulative reward. So you're going to select an action that maximizes the reward, but also maximizes exploration depending on this factor. And also this is configured to seek for risks. Yeah, as mentioned before, the synthetic demonstration are going to be factors that are formed like this with the same formula, and they collected a total of 5 million factorization that are sampled independently and are identically distributed. This is for better training. It does understand. I saw that also in a reinforcement learning book from Morales was the author, I think. And in addition to that, they are gonna pick up the best candidates. The ones that do not perform well are not included in the database. And in addition to the synthetic demonstration, as the training goes, you collect the good moves in a separate database as I showed in the picture. And they use mentioned before, they use change of bases for data augmentation. They randomly generate bases, typically 100,000. And also they use the actions are presented in canonical form to reduce redundancy. This was trained in a TPU. For the training, it was done in a TPU version 3 with a batch size of 2048 and a total of 64 TPU cores with 600,000 interactions. And in the part of the actor, the part of generating the experiences, it was done in a separate TPU, version 4, with 1,600 actors. So there's heavy parallelization in both the experience generation and also the training of the network, but they are done separately. And this takes, they mentioned that it took a week to converge. So now let's go back to the network. The input is a tensor, the 3D tensor, which represents the matrix multiplication, and the torso is gonna basically get you the embedding. And as mentioned before, the grids, you're gonna have 3 grids representing the 3 possible pairs of the dimensions. And the policy head is gonna use an autoregressive policy, And the transformer conditions, basically the cross attention is going to pay attention to the embedding and previous value as mentioned before. And this of feeding the previous value, understand that is called teacher forcing, because it depends only the prediction of token depends only on the previous tokens. Okay. Yeah, this detail already mentioned that the first step without previous step is gonna use to compute the value head, and the value head predicts the distribution of returns from the states, and also they encourage the agent. The way that they achieve this risk-seeking behavior is by predicting the average of the quantiles over 75%. A limitation of alpha tensor is that they have a discrete set of factor entries, -2, -1, 0, 1, and 2. And of course you need that, because otherwise the state space will be huge and probably this will not be able to converge. But also you might be missing out of algorithms that could be better than the ones that they found. So a future research direction could be find this optimal set of factors for the decomposition. And alpha tensor has the flexibility to support complex stochastic and non-differentiable rewards, something that you cannot do in classic supervised deep learning. So you can apply to other problems such as finite fields that I briefly mentioned. And also there you can easily add other metrics to the reward function, like numerical stability of energy usage. So some of the conclusions that we can draw out of this is that alpha tensor is a reinforcement learning agent that improved AlphaGo, and I was able to improve, equal or improve the algorithms for matrix multiplication using the composition. And it was easy to set up the rewards and goals, and some of them might not be differentiable, which it will be hard or impossible for supervised deep learning. Alpha tensor uses a combination of synthetic games and generated games experiences as part of its training, and combining both strategies more efficient than using them individually from the experience of the authors of this paper. The agent is configured to take high risk by using the 75% quantile, the average above that, and while optimizing for reward function, and also they do exploration and optimize for the particular hardware target runtime without knowing anything about it. And within mathematics, reinforcement learning was applied, for example, for theorem proving, finding counterexample to refute conjectures in combinatorics and graph theory. Okay, so that's all I have today. Thank you very much.